Hello, my name is Myson Burch. I am a PhD student at Purdue University studying computer science and currently am an intern at IBM TJ Watson Research Center on the computational genomics team. Today I'm discussing the impact of using polygenic risk scores to predict complex diseases. So, predictive analytics have been used to improve healthcare by reinforcing decision-making, enhancing patient outcomes, and providing relief for the healthcare system. These methods help pave the way towards diagnosis, cure, and ultimately prediction and prevention of complex disorders. Towards that end, diagnosis data and polygenic risk scores can be leveraged to predict levels of disease risk for individuals. Polygenic risk scores, or PRS, measures an individual's genetic predisposition for a particular disorder and is often estimated as the sum of risk alleles weighed by the effect sizes obtained from genome-wide association studies. And in our work, we explore how combining that diagnosis data and PRS scores can contribute to predicting disease risk for binary phenotypes. So here's an illustration for the data that we used here. So we used about 330,000 unrelated individuals of European ancestry from the UK Biobank. And as for gathering the phenotypes or which diseases that we're going to look at, we use natural language processing and manual curation to generate about 411 phenotype items by mapping the ICD-10 diagnoses from the UK Biobank to more meaningful phenotypes, which we clustered in a more interpretable and meaningful way, which is how we got to our 411 phenotypes. We also removed any phenotypes or diagnoses that were in categories that were dominated by non-genetic causes, such as infectious diseases, injuries, poisonings, and pregnancy complications. So this resulted in about 4,000 ICD-10 codes being mapped down to the 411 phenotypes that we started to work with. And out of those disorders, we analyzed 20 different complex disorders for which recent large genome-wide association studies were available in order to generate PRS scores. We generated PRS for those 20 aforementioned disorders using publicly available GWAS summary statistics and UK Biobank data, using various methods such as PRS-CS and SBLUP. After correcting for linkage disequilibrium and strength of association in the GWAS studies. So on the side of the predictive analytics, here's the flowchart of the ensemble modeling that we used. And so, what are ensemble models and why are we using them? So we use ensemble classifiers in order to improve the predictive performance of classification problems by combining the predictions of multiple baseline algorithms. It's also a really nice way to combine the analytics of different problem sets. So since we're dealing with two different types of data here in the comorbidity data and the polygenic risk scores, it's a nice way to combine the predictive performances of both data sets while also weighing them equally still in our analysis. And so we take advantage of the capabilities of well-performing models on classification or regression tasks and make predictions that have better performance than any single algorithm on its own. And we, like I was saying before, we build those models solely using binary diagnosis data, which is the comorbidity data, as well as models that rely exclusively on PRS and combining the predictions to generate more powerful predictions. Unlike traditional GWAS studies, where increasing the sample size increases the power of the study, in this case, additional samples often cause class imbalance, leading to more false positives in a classification task. So we perform class balancing in the training and test sets by matching controls with equal number of cases, while also correcting for the distributions of age and gender in those balanced classes. We randomly sampled 100 individuals, 50 cases and 50 controls to include in the test set, while the remainder of the samples were assigned to the training set. So we applied that Ensemble Framework to the comorbidity data and the polygenic risk scores extracted for the 20 disorders that we wanted to analyze, and here are some results for a handful of those disorders. So we observed that our ensemble evaluated on a variety of phenotypes improved upon the F1 score of the base learners. We can see a larger increase in F1 score for heart failure and diabetes, but a more marginal improvement for the for obesity and kidney disease. What I have in parentheses in the ensemble column of F1 scores is the improvement or lack thereof compared to the best F1 score for any of the base learners. So even though we don't see as good of an improvement for obesity and kidney disease compared to the best base learner, it still is a marginal improvement compared to the other base learners. And so using polygenic risk score as a predictor by itself vastly underperforms compared to the base classifier that only uses comorbidity information, showing the power of association between various disorders in a predictive task. Interestingly, combining the polygenic risk score information and comorbidity information in an ensemble, we observed the PRS consistently improves upon the F1 score, and this was a behavior we saw across the other disorders as well. So in conclusion, predictive analytics is an impactful tool that is becoming more relevant in the domain of healthcare. Using modeling and forecasting techniques, we can add considerable value to healthcare and precision medicine strategies. And here we showed a framework that can aid clinical diagnosis for complex diseases and can also be used to impute phenotypes, thus improving the power of genome-wide association studies. And in future extensions of this work, we would like to incorporate genomic data additional to polygenic risk scores to see how that impacts these models as well. Also, generally improving the base learners for PRS could provide significant improvement for the ensemble. Lastly, I'd like to thank and acknowledge my co-authors and contributors here. I would also like to thank the ISCB for inviting me here to present my work. Thank you so much for listening to my talk. Feel free to reach out to me or find me at the conference for any questions. Thank you.